Hello, Sioux High Earth Science students. This is Mr. McLeod again. Welcome to our next astronomy podcast. Today we'll be exploring how stars, like our sun, are formed and some of the basic characteristics all stars have in common. So have your notebook handy and a pen or pencil, and let's do this thing. As always, there'll be some questions for you in Moodle at the end of this podcast. So make sure you get those done and submitted as soon as possible. Also remember, you can pause or rewind this podcast at any time if you missed something. Okay, let's get started. Here is a picture of a typical star. In fact, this one is probably a picture of our star, the sun. Let's take some notes. So I want you to write that our sun is a small to medium-sized star located about 93 million miles away from the Earth, depending on the season. So go ahead and write that now. Also write that it's made mostly of two gases, hydrogen and helium. Now we'll talk about why just hydrogen and helium later in the class, and the relationship between these two elemental gases as well. But make sure to get this in your notes. As you know, our sun gives off a tremendous amount of energy, and this is in the form of electromagnetic radiation. So get that in your notes right now. Now this radiation reaches us in the form of different transverse waves with different wavelengths. Get this down in your notes as well. I would also like you to make a diagram similar to the one that you see here in this slide. And make sure you label the diagram correctly with crests, troughs, amplitude, and wavelength, just like it is here. Now I'd also like you to add one thing that isn't here. I'd like you to add now the midpoint. So this line right here is referred to as the midpoint. So make sure you label it here on your diagram. The midpoint. Here we see a diagram of all the wavelengths emitted by our sun. Now take a look at this diagram and locate where visible light is on this scale. You'll see it right in the middle right. So look for visible light. Write down that this is the light that allows us to see objects both here on Earth and in the night sky as well. Now we're going to use visible light as a starting point on this scale. So make sure you find visible light. So here it is right here on this diagram. Here's our visible light. Also write in your notes that the wavelengths of the kinds of radiation to the right of visible line of light are all shorter or closer together and therefore have more energy. So we're talking now about these forms of radiation. See here that it says they have high frequency, and we also know that they have shorter wavelengths. We can see that right here as well. Therefore, more energy. So make sure you get that in your notes. Now, also in your notes, write that the wavelengths of the kind of radiation to the left of visible light are longer or further apart, and therefore they have less energy. So now we're talking about these forms of radiation on the left, and we're going to see that these have low frequency, and we can also see that it has longer wavelengths. If we compare the wavelengths of the right-hand side to the left, these are much longer. And if they're much longer, they have less energy. So write that in your notes. Another thing to get down in your notes. Because these forms of radiation are not forms of visible light, we can't see them. So because these are not forms of visible light, we can't see them. And that doesn't mean we can't tell they're there. We just can't see them with our eyes. Our eyes can't detect those wavelengths. So make sure you get that in your notes. Now, next thing to get in your notes. I'd like you to write 2 examples of radiation more energetic than visible light. More energetic, that's over here on this side, and 2 forms that are less energetic than visible. Those would be these forms on the left-hand side. So make sure you get examples of those in your notes. Now let's talk about the color of the visible light. We're now up here in visible light again, and we're talking about these colors of the spectrum. Now, each color in the spectrum has a different wavelength. Write that in your notes. It's the wavelength that causes your eye to see different colors. So write that down. Now, I want you to also remember our discussion of blue and red shift. Now, write down in your notes that the blue end of the spectrum has shorter wavelengths. So over here, this blue end of the spectrum, right here, we can see now has shorter wavelengths. Now, that also means that those forms of light in the shorter wavelength are the most energetic. So get that down in your notes. Now, conversely, if we look at the red end of the spectrum, that's this end over here, we see that they have longer wavelengths. Longer wavelengths means less energy. So the red end of the spectrum wavelengths have less energy. So make sure you get that in your notes as well. Okay, now let's start talking about where stars come from and how they are formed. Now, all of this information that we're going to talk about, we can apply directly to the formation of our sun, which is a star. People frequently forget that our sun is a typical star. Now, here we see a picture of the columns of hydrogen gas and dust that make up stars. These are called nebulae, also referred to as a stellar nursery. Get that down in your notes. Now, whenever you see the word stellar, you know that we're talking about the word star. So when we talk about a stellar nursery, we're talking about where stars are born. And stars are born in places called nebulae. Nebulae. Now, Space is full of these huge columns of hydrogen gas and dust. Recall that this gas and dust was formed from the matter contained in the singularity that formed the mass from the Big Bang. So get that in your notes as well. Now, this slide shows another cloud of gas and dust from which stars like our sun have formed. In your notes, write that the dust we are talking about is mostly made of carbon and silicon. So that write in your notes that the dust that we're talking about is mostly carbon and silicon. Now a word about what happens in the core or center of stars. So write that the center of a star is referred to as its core. Now, nuclear fusion occurs in the core of stars, and I'd like you to write that down. Now, what this means is that hydrogen atoms are fused together to form helium atoms. Now, it takes two hydrogens to make a helium. So write that down in your notes. Now, when two hydrogen atoms are fused together to form a helium, nuclear energy is released in the process. This is referred to as electromagnetic energy. So write that in your notes. So this energy we just talked about and looked at the spectrum and all the parts of it, all come from the core of stars through a process called fusion at the core of the star. Now, our star is emitting large amounts of electromagnetic radiation. And you now know that part of that radiation is visible light. Now, let's think about this. Large amounts of electromagnetic radiation, which means large amounts of visible light. This is why we refer to stars as the fact that they shine. The shining is the light generated from the fusion in the core that we can actually see. And as long as there's fusion in the core of stars, they'll continue to shine. So write that down in your notes. Also remember that the gases that make up that star determine what color that star is. Write that in your notes. That the gases that make up the core of the star, or what the star is made of, determine the color that it shines. In the case of our own sun, it's the hydrogen fusing into helium that gives our sun its yellowish tint. Make sure you get that in your notes as well. Now, for future use, write in your notes that the size of a star determines the amount of radiation they emit. The size of the star determines the amount of radiation they emit. Now, because our star is a small to medium-sized star, it doesn't emit nearly the radiation as some of the giant stars in our galaxy and universe. Stars actually exist due to a surprisingly sensitive balancing act between two opposing forces, or opposite forces. The first one is gravity, which pulls inward on the star, and thermal or heat pressure from the energy released in the core that pushes outward on the star. Write that down in your notes right now. It's a balancing act between gravity, which pulls inward on the star, and thermal or heat pressure from energy released in the core that pushes outward on the star. Next thing to write in your notes. As long as these two forces are equal, meaning gravity and thermal pressure that you see here in this slide, a star will maintain its round shape and will continue to shine as brightly as it can. Write that down. As long as these forces are equal, meaning gravity and the thermal pressure, a star maintains its round shape and will continue to shine as brightly as it can. Now here's the conclusion we want to make. What this really means is that, and write this down, as long as the star has enough hydrogen in its core to fuse into helium, it will continue to shine as brightly as it can. Write that down. As long as the star has enough hydrogen in its core to fuse into helium, it will continue to shine as brightly as it can. That's conclusion number 1. Conclusion number 2. It's when the hydrogen begins to get burned up that stars change how they look and how they shine. We refer to this as a star burning itself out. So write that down. It's when the hydrogen begins to get burned up or changed into helium that stars change how they look and how they shine. We refer to this as a star burning itself out. More about this soon in the next podcast. So now go to Moodle, answer some questions, and get those submitted. Talk to you soon.